Okay, today we'll talk about definite integration. Okay, starting with number 1, we have a couple of ways we can do this. The first one, normally it's a great idea to move any variable that you have. Let's move that to the outside. So it's going to be 3 times whatever we get when we integrate. Now here, our process, we're going to have 3 times. Now to integrate this, we'll lose these signs here, and then we're going to say x, and we're going to add 1 to the current exponent, and whatever that amount is, that's what we divide by. And then we're going to put a bar here, and we're going to say that we're evaluating from 0 to 1. So we're going to have 3 times, and this is going to be x squared over 2, evaluated from 0 to 1. And you can even move this 2 out if you want to. Do keep in mind it's in the denominator. So you have 3 halves times, and then you're going to plug in your top endpoint, and then it's going to be minus, and then plug in your bottom endpoint. So notice here our final answer is just going to be 3 halves. But a lot of times this process here, that's called your B minus A, because your top endpoint is considered B and the bottom A. Alright, moving on to our next example. And again, it's that same process over and over and over. So here, there's really nothing fancy about this. X minus 5 in parentheses just means they want us to make sure that we integrate all of it. So we will. And here again, that's going to be x to the 1 plus 1. That tells me the value I need to divide by. But now we have minus 5. And here, keep in mind, we're doing our antiderivative here. So that's really just going to be a 5x. And then we're going to integrate all of that from negative 2 to 3. So we're ready to start plugging in. And so we're going to have 3 squared over 2 minus 5 times 3. So do make sure you plug into both places with x. So there's your top minus the bottom. So here it's going to be negative 2 all squared. So we know that's going to become a positive. Minus 5 times negative 2. And so finishing this, that's going to be 9 halves minus 15 minus, and this is 4 halves plus 10. Now I left that 4 halves because I know that I'm eventually going to have to combine these, and I would go ahead and not find here and then here, but I would go ahead and separate this and say 9 halves minus 4 halves. So I know that I have 5 halves. And then negative 15 minus 10, that's negative 25. So you're only going to deal with your fraction one time. So this is really going to be 5 halves minus 50 over 2. So I get negative 45 over 2. Right? And so for the last one, again, same process. So again, we're going to go through and we do our antiderivative for each part and then plug in our endpoints. So if we do that, I'm going to have x cubed over 3 plus, and that's going to be 2x squared over 2 minus x. And again, I'm going to evaluate every bit of this from negative 1 to 4. So we're going to plug in 4. So I'm going to have 64 over 3 plus those 2's will cancel, so that's good. 4 squared is 16 minus 4. And then minus, and now we got to plug in a negative 1. So we're going to have negative 1/3 plus 1. And then again, minus a negative 1, so plus 1. And again, I would put together the fractions, then the whole numbers. So I have 64 minus a negative 1/3. So that's 65 thirds. This is going to give us 12. And then minus 2. So that's going to give us 10. And so finding a common denominator here, that's going to be 65 thirds plus 30 over 3. And so we end up here with 95 over 3. Sometimes, like in number 4, we're going to have to do some rewriting, just like we did when we first started our power rule. And for this one, we're going to need to FOIL out what we have. So in our rewriting, again, we're from 0 to 2. But when we FOIL this, remember, you're going to end up with 4x squared minus 20x plus 25. And then we are ready to do our integration process. So here we're going to have 4x to the third, and that's what we divide by, minus 20x to the second, and that's, again, we divide by 2, plus 25x. And again, all of that's evaluated from 0 to 2. So when we plug in our 2, we're going to have 2 cubed, which is 8. 8 times 4 is 32. So I have 32 over 3. I would definitely cancel there, and so I'm going to have minus 2 squared times 10, so 40, and then plus 50. And then if we plug in our 0, since every term has an x, that goes out to 0, so that was nice. So we have 32 over 3 plus 10. So we know that we're going to have, if we change this, that's going to be 3 on bottom and 30 on top. So we have 62 over 3. Again, the rewriting process here for number 5. Same idea. We do need to rewrite this before we start anything else. So again, we're from negative 2 to 3. 4x to the negative 2 plus 1. So now we're starting to see some negative exponents, and we'll go through the same process with that. So we're going to have here, when we start doing our antiderivative, we're going to add 1 to that exponent. So that means I have 4x to the negative 1 over negative 1 plus x. And I'm going to evaluate this from negative 2 to 3. Now we're ready to start substituting in our endpoints. So here a little bit of, well, let's rewrite it first so we can see where things go. Here that's going to be a negative 4, but do remember a negative exponent means we're going to flip that over, and then we have plus x. And we're still evaluating from negative 2 to 3. So that might help a little bit, not to skip that step. Plugging in. So here we're going to have negative 4 thirds plus 3, and then minus, and plug in negative 2. So we're going to have negative 4 over negative 2 minus 2. And so let's see, it looks like some of this might not go away as easily as the previous one. So I'm just going to bring that down, minus, and of course that's going to go to positive 2. So that's going to go to a 0. So that did work out nicely. And of course we do need to get our common denominator, which is 3. So we know 9 over 3 is 3. So it looks like we're going to end up with 5 thirds. Okay, with number 6, again, same process. I would do some rewriting before anything else. So let's integrate from negative 2 to negative 1. X minus x to the negative 2. And again, integrating, let's go ahead and do our antiderivative. So we're going to have x to the second over 2 minus, and if I add 1 to negative 2, I get negative 1, which is what our denominator will be. And then we're evaluating from negative 2 to negative 1. And I would clean up some of this first. So I have x squared over 2, and it looks like we're going to end up with plus 1 over x. And we're evaluating from negative 2 to negative 1. Now we're ready to substitute in our endpoints. And so here, plugging in negative 1 squared is going to give me 1. and then plus, but 1 over negative 1 is going to give us minus 1. Now plug in 2, we're going to have 4 over 2, and then we're going to have minus 1 over 2. All right, so let's see, we've got a 1/2. That's going to give us negative 5/2. So I'm just going to bring all of this down because I'm trying to figure out what would be the easiest way to do these. I know that's going to be 3/2 there. And so 1/2 minus 3/2, that's negative 2/2. So negative 2/2 is going to be a negative 1. And then we already had that negative 1, so it looks like we're going to get negative 2 there. Now you're welcome to do that in any order, but again, whichever way you see best. Okay, continuing on with the rewriting process. And again, here's another great example of where rewriting is going to help us for sure. Let's go ahead and change that denominator. I know that's going to be x to the 1/2. And we can move it up or we can divide. Either way, let me show you. From 1 to 9, we can say this is x over x to the 1/2 minus 2 over x to the 1/2. Now we're allowed to do that as long as you have one term in the bottom. Now if you have more than one term in the denominator, don't do this. It won't work. So now we can subtract our exponents. So we're still integrating from 1 to 9. Do remember it's top exponent minus bottom. So 1 minus 1/2 is positive 1/2. And then minus, and we know this is going to flip up. So that's going to be 2x to the negative 1/2. And then we're going to integrate all of that. And so now we're ready for our antiderivative. So we're going to add 1. And do remember our shortcut. If we're adding 1 here to that exponent, you're really saying 1 plus 2, which is 3. So this is x to the 3/2. And then that's over 3/2, because that, again, that tells us what that denominator is going to be. Minus 2 times x to the, and again, if I add 1, that's going to give me a positive 1/2, which says this is over 1/2. And I'm evaluating all that gobbledygook from 1 to 9. So here in our simplifying, do remember you are dividing these fractions, so you do multiply by the reciprocal. So this really does end up every time the coefficient being multiplied is going to be the reciprocal of the exponent that you just generated. And so over here, minus, since that 2's already there, you're just going to multiply it with the other 2. When you divide, you're going to flip over that fraction. So you have 4x to the 1/2. And now we're integrating from 1 to 9. So let's go ahead and plug in. So for this first one, we're going to have 2/3 times 9 to the 3/2. And this is non-calculator, so we're going to review how to do that. That's 9 raised to the 1/2 minus our bottom endpoint, and we're just substituting in a 1. So 1 raised to whatever power is still 1. So basically I've got my coefficients here, 2/3 minus 4. Now let's review how to do this rational exponent. So here we're going to have 2/3 times, the bottom part is our square root, so the square root of 9 is 3, and then 3 to the 3rd power is 27, minus 4 times, and again that bottom, that 2 is square root, so the square root of 9 is 3, 3 to the 1st power is just 3, and then that's all going to be minus 2/3 minus 4. So now we're ready to put together all these numbers, and my gracious, so 27 times 2. I wouldn't cancel the 3 because you're just going to have to find a common denominator over here, or you can, it's up to you. It's not really wrong either way. So here, if I put those together, that's going to give me 54 over 3 minus 12 minus 2/3 minus 4. And so here I'm going to have 54 over 3 minus 2 over 3. So that's going to be 52 over 3. Negative 12 minus a negative 4, or plus 4, that's going to give me negative 8. And so finally, let's see, that 8, if that's over 3, 3 times 8 is 24. So we have 52 minus 24, which I think is probably going to be a 28 over 3. All right, so let's continue on. Same process over here with number 8. We do need to rewrite it, but this time our exponent is going to be a little bit different. We've got to change from the cube root form. Do remember that's an understood 1 under that radical, and so we have negative 2 to 2 of x to the 1/3 power. And now we're ready to do our integrating. You're done with your rewriting. So we're going to add 1. So 1 plus 3 is 4. So I have 4/3. And if I divide by 4/3, I'm really multiplying by 3/4. And I'm integrating from negative 2 to 2. So let's see what we have here. We're going to have 3/4 times, and we have here positive 2 raised to the 4/3. And then we're going to have minus, and then we're going to have the same thing, but we're going to have 3/4 times negative 2 raised to the 4/3. Now we can do this. Remember, cube root is fine. So this is going to be the cube root of, let's put this together. We have 3/4, and this is going to be times the cube root of 2 to the 4th minus 3/4 of, let's say, the cube root here of negative 2 is still going to be a negative that we can pull out. So let's see, we've got the 3rd root of negative 2 to the 4th. So what's going to happen here is we actually have a positive version, and then right here, whenever I square or raise to the 4th this portion here, it's going to go to a positive as well. So that 4th root here, let me rewrite it so we can see what's going on. What'll happen is we have 3/4 times the cube root of 2 to the 4th minus, and that negative 2 is raised to the 4th, so that negative is going to disappear as well. So notice we have 0 for our total bounded region or volume or area, whichever it's finding. But a good note for us to realize here, though, is the graph. If we look at our graph of x to the 1/3, and this is one of those basic parent functions that we learned back in Algebra 2, right here. Pretend that went through the origin, folks. So this is x to the 1/3, or the cube root of x. This is an odd function. So what's unique about odd functions is if you're going from negative 2 to positive 2, or negative 3 to positive 3, or negative 5 million to positive 5 million, you're guaranteed the same amount of bounded region on top as bottom, and they'll always cancel each other out. And that's why I'm showing you this, is because if you have an odd function with the same endpoints, that area will cancel each other out, and your answer is always going to be 0. And that's pretty useful to remember. If you see odd functions, that's going to help you with that. So if you were integrating x cubed over the same interval from negative 2 to 2, you're still going to get a 0 there. Any of those odd functions are going to do that to you. Cosine and sine. Sine is an odd function, so if we integrated from, let's say, negative pi over 2, or negative pi, or pi over 2, to the same amount up here of sine x dx, that's going to give us a 0 because sine is an odd function. All right, moving on to our next function, or next problem. Same process again. we are going to be adding here to that exponent. There's no rewriting necessary. It's already been rewritten for us. And so let's see with this. I'm going to add 1 to my exponent. So that's going to make this t to the 2 plus 3, 5/3. But then I'm dividing by that, so I need to multiply by the reciprocal. Minus same thing over here. So this is going to be t to the 4/3. And then that coefficient is going to be 3/4. And this is evaluated from 0 to 1. And so if I plug in 1, well, that's nice, because plugging in a 1, that's just going to generate these coefficients. So I'm going to have 3/5 minus 3/4. And then if I plug in 0, my other endpoint, everything has a t in it, so that's going to go to a 0. So a quick reminder on how to do these. Now the super quick way, multiply your denominators and then cross multiply. So you have 12 minus 15. So we end up with -3/20. Now for our next problem, we're going to have to do something a little different with it. The problem is our absolute value function. If we sketch this, and it's a good idea for us to, we know an absolute value is in the shape of a V, and we know for this particular function we've moved 2 places left. So I have something that looks like this. Now, students always ask if they can just find this bounded area here and here, and yeah, you certainly can. That's one way to do it, because you can divide that up into 2 triangles and do 1/2 base times height and go through your process there. Or we're going to have to divide this up, because at this particular point, at x equals 2, we are not differentiable. Now what that means is, if you're not differentiable, you were not able to take the derivative there. Well, if you wasn't able to take the derivative there, you can't do the antiderivative, because the derivative didn't exist to begin with. So we're going to have to divide this up. So to divide this up algebraically, what we will do is, we know from 0, because that's where we're starting, up until 2, we're going to have a certain area. And then over here, after 2 up till 3, we're going to have a certain area. So our 2 integrals are going to be from 0 to 2 of something. And then I'm going to add to that from 2 to 3. And that's going to capture these bounded regions here and here. Now, what am I going to integrate? I cannot use our absolute value. So what I need is really the equation of this line over here. And it's super easy to find. Notice that the slope of this line is going to be negative, because from left to right it is decreasing, so slope is negative. So to achieve that, all you need to do is change places with 2 and x. So really on this one, you're integrating to minus x. And notice that negative x, remember the coefficient of x is your slope, and that's going to generate the right slope for us. Now on the other side of 2, so now we're increasing, and so we need to keep exactly the same form that we had. So this side we're going to integrate from our x minus 2 dx. And so there's how you divide this up. And now the rest of this problem is worked just like all the others. You just have a couple of things to go through the integration process with. So to go through our integral, we're going to find our antiderivative. So we know that's going to be 2x, because I need to put an x there, minus x squared over 2. And again, all of that's evaluated from 0 to 2. And then plus, and then over here we're going to have x squared over 2 minus 2x. And this one is integrated from 2 to 3. So let's go ahead and do our plugging in. And whenever I plug in, I'm going to have 4 minus, and that's going to give us 4 over 2, so 2. And then our other endpoint is 0, so that's nice. Plus, and then over here we're going to have 9/2 minus 6. minus, and then plug in our 2, we're going to have 2 squared 4, 4 over 2 is 2, minus 4. So in this parentheses we got 2 plus, and then over here we have 9/2, and I save those fractions till the end. I'm going to avoid them like the plague. Minus, and then 2 minus 4 is -2. So I can put together my whole numbers here. I'm going to have 2 plus 2 is 4, 4 minus 6, -2. So I have 9/2 minus 2. So that's really 9/2 minus 4 over 2, which is going to get us 5/2, which should be, if those of you went through and wanted to find 1/2 base times height on each side, just add that bounded area, and it should generate the same thing for us. Now we're going to integrate some trig functions. That's going to start popping up. Now again, go back to what we learned very beginning when we were doing derivatives. We have sine, cosine, negative sine, negative cosine. We knew going down this chain that was your derivative, which is your slope. But now we're moving up, which is the antiderivative, which is going to be area. That's the application of it. So we're at cosine, and I need to integrate. So from cosine, we're moving up because it is an antiderivative that we're doing. So we're going to be at sine. So really this is going to say sine x, and I'm integrating that from -pi/2 to +pi/2. And so we're going to plug in, and sine of pi/2, and this is usually where y'all are like, nope, I'm done, I don't remember. You need to learn these. Now, sine at pi/2, that's, if you review, pi/2 is up here, -pi/2 is down here, sine is your y value, so you're talking about 1 and -1. Sine of pi/2 is 1, then minus, sine of -pi/2 is -1, so notice we get an area of 2. So notice this had the same or opposite endpoints. Well, cosine is an even function. So cosine of x, that's an even function. Just like if you talked about doing a parabola, all those even functions, they're all mirror images over the y-axis. So just like that, x squared is also even. Now what that means is if we just wanted to integrate from 0 to pi/2 and then double that answer, that would have given us the same exact answer. So either way you want to do those is up to you. But again, that only works nice and neatly whenever you have congruent or opposite endpoints. All right, for our next one, again, same process. So if I integrate 2x, that should give us x squared. And then minus, and if I integrate sine, again, if you're not sure, there's nothing wrong with writing this. You're at sine, you're integrating, so you're moving up, so you're going to wrap around to negative cosine. So that negative is going to cancel out this negative, so I'm going to have cosine x. I'm going to evaluate this from 0 to pi. And so we're going to have pi squared plus cosine of pi, and then minus 0 plus cosine of 0. And pi squared, leave that in exact form. Cosine of pi is -1 minus, and then over here 0, of course, is 0, but cosine of 0 is 1. So it looks like we get pi squared minus 2 for this one. Okay, some more trig practice with this. And again, you had sine, cosine, negative cosine. And so here that 3, again, that's just 3 times whatever we get when we do the antiderivative. So writing this out, that's going to be 3 times. Well, the antiderivative of sine is going to be negative cosine, so I'm going to put a negative and then cosine x minus 2 times. And if I integrate cosine, I'm going to get sine x, and all of this is evaluated from 0 to pi/2. So substituting in our values, we have negative 3 cosine pi over 2 minus 2 sine pi over 2. Okay, and now we're going to do minus, and we're now going to substitute in 0. So I have negative 3 cosine 0 minus 2 sine 0. All right, so here cosine of pi over 2 is 0. So for this one, we're going to have 0 minus sine of pi over 2 is 1. So 2 times 1 is 2. Minus, here cosine of 0 is 1. So we have negative 3 minus sine of 0 is 0. So we have negative 2 minus a negative 3. So we end up with 1. All right, so what about secant squared here? Now, keep in mind, you're asking yourself, I took the derivative of something, and that something gave me secant squared x. That's what this is asking, and hopefully we remember that the derivative of tangent x is secant squared x. So when we start doing our antiderivative, do keep in mind you're working backwards. Please don't be intimidated, because if you learned all of them first semester, you're just working backwards, and it's okay to ask yourself this. Go over to the side and do what I just did. So if I go through this process now, well, I know this is going to be x squared over 2 minus tangent x, and then I'm evaluating this from 0 to pi over 4. And so substituting in, we're going to have pi squared over 4 squared, which is 16, and then all of that gobbledygooks over 2, and then minus tangent of pi over 4. Tangent of pi over 4, I think, is 1. Pretty sure of that. And then we're going to substitute in 0, and tangent of 0 is 0, and 0 squared over 2 is still 0. So we just have to figure out this terrible looking fraction, but we know that means divided by 2, so multiplied by a half. So that's pi squared over 32 minus tangent of pi over 4 is 1. So this is really going to be pi squared, and you know, you can leave it. Let's just leave it like this. This is how you would see it on a multiple choice anyway. So I wouldn't bother doing too much more with that. All right, number 15 always gets people as well. They're like, oh no, what is this? I don't remember. But again, go over to the side and ask yourselves, back during the first semester, we did the derivative of something, and the derivative of that something gave me secant theta, tangent theta. And so hopefully we see that that something was just secant theta. So when I integrate all of that, it goes to secant theta. And you're evaluating this from 0 to pi over 3. Now we're going to substitute in secant pi over 3 minus secant of 0. Now we do need to remember secant is the reciprocal, secant of theta is 1 over cosine of theta. So that's helpful. Now, if we only knew what cosine of pi over 3 is, well, cosine of pi over 3 is 1/2. So if I do the reciprocal of 1/2, I get 2 minus, and secant of 0, well, if I knew cosine of 0, that would help. Well, cosine of 0 is 1, so the reciprocal of 1 is 1, and 2 minus 1 is 1.